Hopefully by the end of this section, you will be able to calculate the union of two sets, the difference of two sets, and the intersection of two sets using theorems 9.3.1, 9.3.2, and 9.3.3. This is counting elements of disjoint sets using the addition rule. Section starts with 9.3.1, the addition rule. Okay, so it talks about how to find the cardinality of a set that's made up of k distinct mutually disjoint sets. It says that the cardinality of A is going to be the cardinality of A1 plus A2 and so on and so forth. Now, let's explain what this thing is and let's break it down one step at a time. Suppose that we have three sets A1, A2, and A3, which are 1, 2, 3, 4, and 5, 6. First of all, what would the union of all those sets be? So what would A1 union A2 union A3 look like? Well, it would be 1, 2, 3, 4, 5, and 6. Now keep in mind that A1, A2, and A3 are themselves mutually disjoint. Now that term is kind of tricky. We've already described it once in chapter 6, but in case you forgot, disjoint means that they have no common elements. And mutually disjoint just means that it doesn't matter which combo you take, the combo you choose have nothing in common. So it doesn't matter if I choose A1 and A2, or A2 and A3, or A1 with A3. Regardless of my choices, the elements inside look different always. So that's what it means to say mutually disjoint. Now the question is, if I call the union capital A, how big is capital A? What's the cardinality? How many elements does it have inside? Well, you can see it right here. It's got 6 elements. What's another way of calculating this? According to the theorem, since my sets were mutually disjoint, I could just calculate how many elements there were in A1, which is 2, how many elements in A2, which is 2, and how many elements in A3, which is also 2, and then add up those numbers. 2 plus 2 plus 2 would be automatically equal to 6 again. Okay, so that's pretty much how the rule works. You have to start off with mutually disjoint sets though. If you don't have mutually disjoint, then you'll have to kind of switch up the rule a little bit and talk about the inclusion-exclusion rule, and that's going to be section 9.3 with theorem 9.3.3. Okay, so for now, let's apply that theorem with example 1. It says, suppose that a password can be made up of either 1 or 2 or 3 letters of the English alphabet. How many passwords could there be? So remember, my password could be either 1 character long, and that's it, or it could be 2 characters long, and that's it, or it could be 3 character long, and that's it. So as you can see, my passwords can be grouped, all the 1-letter passwords, all the 2-letter passwords, and all the 3-letter passwords can be separated. And not a single password will overlap, will be able to transfer from here to there or vice versa. So this is an example of 3 sets that are mutually disjoint. So let's go ahead and write it down. So my password can be made up of either 1 letter or 2 letters or 3 letters. So what I'm going to do next is remind you that these 3 groups, the group of 1-letter passwords and 2-letter passwords and 3-letter passwords, are all disjoint. Okay, so the 3 groups or the sets are mutually disjoint. Okay, so next what I'm going to do is I'm going to count how many 1-letter passwords there are and how many 2-letter passwords there are and so on. And I think it's pretty obvious that there are 26 1-letter passwords. If we're talking about the English alphabet, there are only 26 letters. So that's what we can choose. We're not allowed to pick any digits in this case because they said pick only letters. Now, how about the 2-letter passwords? Well, remember, there's basically 2 choices. And they're not saying repeats are not allowed. They're basically saying anything goes. So I can pick, let's say, B for the first letter. And there are 26 choices for that. And then I got to pick the second letter. How many letters are there? Well, I can choose B again if I want to, or I could choose something else instead. Let's say E. And again, there were 26 choices for that. So for the 2-letter passwords, it's basically 26 to the power of 2. And finally, in the same way, I can figure out that for 3-letter passwords, it's pretty much the same concept except 26 to the power of 3 because there are 3 letters in that case. So now, since the sets were all disjoint and I would like to know how many letters how many passwords there are of 1 or 2 or 3 letters, what I have to do at this point is basically take all the numbers that I just determined and add them up. So the total number of passwords is 26 plus 26 squared plus 26 cubed. So that's an 18,258 cardinality kind of set. So that's the end. At least part 1 is basically finished. All right, so now part 2. It says how many numbers from 100 to 999 are divisible by 5. Okay, we already did this problem before, but I'm just trying to do it in a slightly different way this time, okay? So what I'm going to do for this problem in order to figure out the amount of numbers that are divisible by 5 is this. I'm going to figure out how many numbers end with 0, and I'm going to put them together, and I'm going to figure out how many numbers end with 5, and I'm going to put them together, and figure out if the sets are disjoint or not, then add up the total. Okay, so to be divisible by 5, a number must end with 0 or 5. So let's group all the numbers that end with 0 in one set. Okay, so set A1 is going to be the set of numbers that end with 0, and these are the numbers like 100, 110, and so on, all the way to 990. Okay, that's the last number that ends with 0 that can be divided by 5 out of this list. And then I'm going to do the same thing again with the numbers that end with 5. This time though, I'm calling the set A2. And notice that A1 and A2 are disjoint. So nothing in A1 can also be in A2. A1 and A2 are disjoint. Okay, that means the sets have no overlaps. Their intersection is basically empty. Okay, the sets are disjoint. A1 is 90, and the cardinality of A2 is 90 again, because the first integer can be anything it wants to be except for 0. So it's got to be anything out of the other 9 digits. The second digit can be anything it wants to be. It could be any of the 10 digits. And the third digit has to be either 0 if you're in A1, or it has to be a 5 if you're in A2. So there's only one choice for that. So again, you can put anything you want there, you can put anything you want there, but the third digit is predetermined. It's either 0 or 5. Okay, so that's why there's 90 for the first set and 90 for the second set. And so now the final answer is the total of A is going to be given by the following. The cardinality of A is going to be the cardinality of A1 and cardinality of A2 together. So that's basically 90 plus 90, which is 180. So there are 180 three-digit numbers that can be divided by 5.